Good morning, good afternoon, everyone. Welcome to Keysight Technologies virtual event series. We are pleased to have you here for today's virtual event on harnessing digital twins in wireless design and development. My name is Girish Baliga from Keysight Marketing, and I'm the moderator and presenter at today's webinar. Today, we'll be spending the next 45 minutes or so deep diving into harnessing digital twins in wireless design and development. Before we get started, couple of housekeeping inputs. During the presentation, you can dial in your questions in the Q&A box on the streaming console. We'll be more than happy to answer your questions and get back. Also, please share your recommendations on the survey form, which will appear as a pop-up during the course of the webinar. There is also resource collateral on harnessing digital twins in wireless design and development on the webinar console. You can download this from the resource list. In addition, please share your comments about the program, enabling us to serve you better. And please use audio headset or earphones to listen to the virtual event audio for good audio effect. I'll be presenting today's paper on harnessing digital twins in wireless design and development. I manage the marketing for 5G wireless, wireline, aerospace defense, and software at Keysight Technologies. Without much ado, let us begin the session. All right, let's get started. Let us first understand what is a digital twin. A digital twin is a real-time virtual representation of a real-world physical system or process that serves as a digital counterpart of it for practical purposes such as system simulation, integration, testing, monitoring, and maintenance. So the digital twin concept consists of three distinct parts: the physical product, the digital or the virtual product, and the connections between the two products. The connections between the physical product and the digital or virtual product is the data that flows from the physical product to the digital product, and information that is available from the digital or the virtual product to the physical environment. The digital twins are commonly divided into subtypes that include digital twin prototype or DTP, the digital twin instance or the DTI, and the digital twin aggregate or the DTA. The DTP or the digital twin prototype consists of the designs, analysis, and processes that realize a physical product, whereas the DTP or the digital twin instance exists before there is a physical product. The DTI is the digital twin of each individual instance of the product once it is manufactured. The DTA or the digital twin aggregate is the aggregation of DTIs whose data and information can be used for interrogation about the physical product, prognostics, and learning, and also the specific information which is contained in the digital twins is driven by various use cases. In summary, the digital twin is a logical construct, meaning that the actual data and information may be contained in other applications. Now, let us understand the various characteristics of digital twin technologies that distinguishes digital twins from other technologies. The typical characteristics which we will delve in further detail with respect to digital twins involve connectivity, homogenization, reprogrammability and smartness, digital traces, and modularity. Let us now understand each of these characteristics in greater detail. So let's get started with the connectivity. So one of the main characteristics of digital twin technology is its connectivity. The recent development of IoT or Internet of Things brings forward numerous new technologies. See, the development of IoT also brings forward the development of digital twin technology. This technology shows many characteristics that have similarities with the character of the IoT, namely its connective nature. First and foremost, the technology enables connectivity between the physical component and its digital counterpart, like we kind of delved upon earlier. The basis of digital twins is based on this connection, and without it, digital twin technology would not exist. So digital twin technologies thereby enables increased connectivity between organizations, products, and customers, and it ensures that the members in the supply chain can make use of the digital twin of a product or an asset. Talking about the second characteristic, which is homogenization, digital twins can be further characterized as a digital technology that is both the consequence and an enabler of the homogenization of data. Due to the fact that any type of information or content can now be stored and transmitted in the same digital form, it can be used to create a virtual representation of the product, that is in the form of a digital twin, thus decoupling this information from its physical form. And therefore, the homogenization of data and the decoupling of the information from its physical artifact have allowed digital twins to come into existence. However, digital twins also enable increasingly more information on physical products to be stored digitally, and thus become decoupled from the product itself. The next most important characteristics of digital twins is the reprogrammability and smartness. So specifically talking about this particular characteristics, a digital twin can enable a physical product to be reprogrammable in a certain way. Furthermore, the digital twin is also reprogrammable in an automatic manner through the sensors on the physical product, or using artificial intelligence technologies and machine learning, or even predictive analytics. As a consequence of this reprogrammable nature is the emerging or the emergence of such functionalities. For example, if we specifically look at very specific examples which would help reprogramming a digital tin when required, and this reprogrammability would ensure that the with the coupling with artificial intelligence, it can also offer this as an extra service. The fourth characteristics is about digital traces of digital twin. And this is specifically observed is the fact that the digital twin technologies leave digital traces. These traces can be used by engineers. For example, say if there's a machine or a product which malfunctions, so they need to go back and check the traces of the digital twin to diagnose where the problem occurred. It's kind of a back annotation of sorts. This diagnosis can in the future can also be used by the manufacturer of these products or machines to improve their design, so that the same malfunctions will occur less often in the future. The next important characteristics of digital twin is the modular nature or the modularity. In the sense of the manufacturing industry, modularity can be described as the design and customization of products and production modules. By adding modularity to the manufacturing models, manufacturers gain the ability to tweak models and products and machines. So digital twin technology enables manufacturers to track the products that are used and also the machines and notice possible areas of improvement, so on and so forth on the fly. When the products are made modular using digital twin technologies, manufacturers can see which components from the product would perform poorly and replace this with better fitting components to improve the overall manufacturing processes. One question which is frequently asked is, are digital twins and simulations the same? Given the emerging nature of the digital twin concept, it's quite natural to have this question. While simulation is an important and integral part of digital twins, the purpose of digital twins would stretch beyond simulation. Now, let's understand the three key differences. So, the first one is the past. So, simulations are typically used for design and in certain cases offline optimization, as you can see from the slides. However, digital twins, on the contrary, are used for the entire design, execute, change, decommission life cycle in real time. For example, imagine a car which is driving into a garage for a regular service. Traditionally, the service engineer assigned will interview the car owner and conduct visual checks and download the logs before deciding on the service plan. Now, imagine a virtual model that knows everything about the car up until the moment vital performance statistics are corrected on a regular basis, the parts replaced in the past, previous service records, and potential issues as observed by the sensors and more. In this operational scenario, the digital twins would help deliver time, cost, and effort savings. Every stakeholder stands to benefit from the enhanced and relevant information available at the opportune moment. The second most important piece is the present. Simulations can help understand what may happen in the real world. However, with the digital twins, it not only would help understand what may happen, but crucially what is happening or how the design is behaving in the real world. Anyone, for example, who has sought out for a project status report will understand the trickle of information with the inconsistent updates and the pain of comprehending the data. However, the problem would be multidimensional and a few common reasons are available with respect to timely updates, manual data collection, distance and logistics involved in gathering the information. Now, let us imagine a situation where the real world data via sensors is collated into a virtual model. That is the beauty of the digital twin, is that it offers a real-time view in a human-friendly 3D visual format, and human operators who are monitoring and interpreting the as-is status of large-scale projects would help elaborate the process and equipment and also operational assembly lines, and even for example patients under care will benefit from the timely easy to consume information. In a fast moving world where time is of essence, the real time insights will help prevent many bad decisions, conduct preventive maintenance, and reduce untoward incidents. So the next ballpark figure is the future. Traditional simulations don't provide insights into the interactions with the physical, whereas the digital twins will be a source of understanding of the clashes and conflicts when physical things interact. Organizations usually start their digital journey with the simulations of critical assets, and such simulations are good for playing the what if scenario for the assets. Yet, in the real world, when assets intersect with other products, people, and processes, there arises many undesired and unexpected behaviors. So, digital twins with their view of the real world will help operators to understand the interactions and incorporate that into the simulations. So, at the end of the day, standalone simulations will converge into digital twins for understanding the ways of how a particular product or a solution or a subsystem or a system would work. And like we discussed earlier, digital twin aggregates or DTAs are expected to deliver hitherto unknown insights on the collective, which a standalone simulation cannot. Model-based system engineering or MBSE is a systems engineering methodology that focuses on creating and exploiting models as the primary means of information exchange. Most model-based approaches address four system engineering domains: requirements, architecture, behavior, and verification or validation. With the MBSE tools, it helps tie these domains together virtually using a digital modeling language, leaving the document-centric approaches behind. The digital twin concept hopes to convert most, if not all, of the physical system engineering activities into virtual ones. So, digital twins will have a high value where staging physical testing is hard and real world effects are difficult to reproduce, like in, say, 5G or radar, satellite, or other RF system scenarios. A digital twin would extend the MBSE or the model based systems engineering, which has engineering benefits, even if math based models only approximate the behavioral characteristics of physical prototypes. Dynamic environments can have dramatic effects on the complex wireless system performance. For an example, an instance where the virtual truth about the current state of the physical system should start out good and get better, and closing any accuracy gap. So, moving engineering efforts to virtual space calls for a digital twin sitting on three pillars. As we see from the slide, a virtual prototype which is built around high fidelity models in a functional framework, and simulations providing stimuli and observing matching real world operational conditions, and updates to models and simulation based on feedback from measurements on a physical twin. So, the pathway of system design goes beyond math-based modeling and shift-left thinking. Its robust component models would incorporate the real-world effects with the keysight measurement science, and then aligning the parameters so physical twin measurements feedback to virtual models precisely. And here, libraries would provide a pre-built and verified reference designs for complex wireless specifications along with the simulation stimuli. High level integration further adds a scenario and mission planning information for real world environmental conditions. Multi-domain modeling and simulation would unlock near circuit level accuracy, where replacing real world activities with a digital twin requires a high level of accuracy from the start. Pathway system designs brings wireless multi-domain modeling and simulation to the first two pillars of the digital twin. For example, if we specifically talk about off-the-shelf and extensible behavioral models, over more than 300 simulation blocks come standard, all with the high fidelity wireless characterization which is built in. So this helps that the time domain simulation with the pathway design or pathway system design would capture very specific time varying behavior and addresses the data flow simulation for complex wireless system scenarios and as well as ensure that multi envelope data flow which will handle specific characteristics required for high end wireless designs. So specifically talking about measurement science, using MPSC for wireless system architecture has a big implication and helps in turning inside out for complex RF systems design using MPSC. So when it comes to any complex system, it's difficult and prohibitively expensive, if not impossible to physically recreate everything a system might see in the real world. So engineering in the virtual space makes sense given other factors in wireless system design which are enumerated here are taken care of. For example, as you can see here, requirements often arrive in the form of comprehensive industry specification. Scenarios are very crucial and they define the kinematic and interference effects on the system. Behavioral models are complex but definable under the RF physics detail, and parameters would go hand in hand with the observability and measurement science. So, in summary, MBSC holds the key to earlier and more accurate system capability prediction, which would take digital twin a very long way. So, it also helps integrate with other modeling as well as scenario planning and MBSC tools and workflows. It is pretty challenging to bring real world environments into a digital twin. However, typically when we talk about the complex virus systems that fit into integrate real world environments, the platforms move and reorient, changing the wireless propagation and interference. The system that functions well in a fixed location may display problems when kinematics are introduced. One location may be trouble free while another presents nearby emitters which can cause issues. So in three-dimensional space, problems may come and go as paths cross temporarily. On many of such programs, there are teams of less wireless centric system engineers and planners who are working on modeling these environmental scenarios instead of kind of pushing these teams into all new workflow or creating a discontinuity between their work and that of RF design teams. The pathway system design extends the RF system engineering capability with integration of popular tools for mission and scenario planning, requirement management, as well as high level system modeling. One of the key pillars of the digital twin is to ensure that the performance modeling with the measurements from a physical twin completes the transformation of the virtual prototype into an instance of a physical systems. Two aspects of Keysight measurement science into unrivaled capability does exist for wireless system digital twins. Architecting functional structure for a system like 5G NR type of wireless connectivity or digital modems, as well as advanced wireless systems, usually turns out to be pretty straightforward, especially if there is a consideration of very powerful tools like pathwave system design that has optimal reference libraries for such kind of applications. Design teams can then pull in specification compliant blocks and then add their own HDL code or C++ um, scripts to complete their system. It's not straightforward is the first aspect. The stimuli required for to fully exercise those blocks. Without verified complex waveforms for wireless system specifications, assessing performance and test coverage turns into a lengthy and somewhat risky guessing game. Like you see from the screenshot here, the second aspect is the analysis. Vector modulation analysis is pretty complex, requiring state-of-the-art instrumentation for accurate results and powerful visualization in determining the problems. That's where the Keysight measurement science makes its impact. The same knowledge that Keysight uses to design its instrumentation connects with the past wave system design. The teams can now use the same stimulus in both the simulation and physical lab testing. Results from physical twin measurements can be brought back into modeling for enhancements and further analysis. For instance, a Keysight vector network analyzer offers an efficient way to create and enhance component behavioral models. Its measurement capabilities would ensure that this can be fed back into the simulation environment and it can go to and fro. Similarly, the Keysight pathway vector signal analyzer handles modulation as you can see in the graphic here, including very high-end capabilities like carrier aggregation, higher order MIMO, constellation signal quality analysis, and so on. And depending on the designer's need, especially who are working to and fro between the physical twin and its virtual counterpart, these advanced measurement capabilities can help connect directly with the pathway system design, eliminating guesswork and estimation and increasing the model fidelity. As the specifications evolve, Keysight measurement science continues to grow. Like we discussed before, the all new workflow in pathway system design will help ensure that the reduced discontinuity between engineers who are working on physical designs and those who are working on simulation and modeling. And this is also specifically true for wireless system design. So pathway system design extends the wireless system engineering capability with the integration of popular tools for mission and scenario planning, requirement management, as well as high level systems modeling. Now, teams can drill down into a part of a design, reduce the world level complexity while simulating with higher wireless fidelity using pathway system design, and then keep sharing the results and back annotating, improving the accuracy of its digital twin so that the overall efficiency of the system design is enhanced. So, pathway typically ensures that this particular aspect is taken care of so that if you are specifically talking about the links which are capturing various coupling effects that start early in the system design processes, sharing data with the design and simulation tools, including layout, and highlighting EMI EMC capabilities are becoming pretty seamless with the digital twin scenarios. Teams can explore system and physical design simultaneously with the higher wireless fidelity. Like we discussed earlier, a digital twin is a virtual instance of a physical system which is continually updated with the latter's performance, maintenance, and health status data throughout the physical system's life cycle. So time weighs heavily on electromechanical systems with the degradation, repairs, and upgrades. So electronic systems can typically decouple functional performance from reliability. For either type of system, performance enhanced assessment is in a variety of operational situation is a prime use case for a digital twin. So, engineers often use spreadsheets for fast estimates or lightweight math-based modeling to speed up simulation. As you can see from the graphic here, so one of the key aspects of the MBSE for wireless system architecture has to kind of back annotate into predicting system level capabilities early into the design so that it can be fed back into its digital twin and a more capable uh, output is given leading to reduced errors. So, typically in modeling a complex wireless system, the digital twin has to help reduce the complexity through abstraction and also to ensure that the accuracy is enhanced. See, the overall goal should help package complexity in models that are easier to use in architectural framework without sacrificing fidelity. So, in summary, digital twin technology offers significant value to an organization as it allows continuous access to the discrete digital replica of the physical object and process throughout its life cycle. See, the digital replica can then be used for analysis, which can provide insights into actionable information to improve the overall process or product in terms of optimized performance, cost effectiveness, readiness, and maintenance. So, in summary, what this tells is that the capabilities of digital twinning are going to ensure that it provides a cost effective way to perform analysis, testing, and optimization. And as you can see from the graphic here, Keysight Technologies is in the forefront in providing automated and semi-automated tools for rapidly creating digital twins of physical network. And there are a host of such models which are available, which can be made use of to extend and perform the analysis for any type of electronic systems. Dear participants, we hope this session was helpful to you. This session would also be available on demand shortly so that you can go through this virtual event again. On behalf of Keysight Technologies, we would like to thank you for participating in this session. As you may know, Keysight Technologies runs a series of virtual events periodically, and we'll keep you posted on the next set of virtual events over email and other modes. This virtual event will also be available on demand shortly, and you will get an email once it is ready at the address you would have used for registration. You can view this virtual event any number of times on demand. You can also share the on-demand details with your colleagues, team members, friends, etc., enabling them to register and participate. With that, we would like to sign off this virtual event. All of you have a nice day. Thank you and bye.